for those who don't know me yet, my name is Roman. I'm Head of Engineering at SDC Verifier. So today I'm going to cover the 2 days webinar, which is dedicated to port equipment verification and validation. So I'm going to turn off my camera just to make connection smoother and basically show slides themselves. Just a second. Yeah, and then we swap. Okay, so this is the short agenda of the 2 days webinar. We will start from a very short introduction on the background for those who don't know yet. Basically, after that, we will talk about the main challenges with port equipment verification, touching the base of fault structures and calculation methods. We'll also cover the importance of FEA with use case examples, and also how to make FEA projects according to industry standards, how to streamline your workflow, basically some effective techniques to save time and reduce costs. We've also briefly talk about the FEA tools, structural asset management, summary, and a short Q&A session in the end. So basically, if you will have questions during this webinar, feel free to just drop them in a chat, and then in the end we will cover them. So who we are? The company itself was founded in 1998 as a consultancy engineering services company. So we have so far 26 years of experience. Basically, over the past 10 years, we finished more than 250 consultancy projects with over 100 happy customers around the world. But then since 2008, we have been developing our software. This is a code checking software, which over 200 companies are currently using around the world in multiple industries. And basically, in addition to embedded post-processing capabilities, now we have developed a standalone tool, which we will also briefly discuss today. So, like I mentioned, we have more than 200 happy customers around the world using SDC Verifier, which you can briefly see on this screen. Well, not all of them main ones, but I think that gives a good idea. The same we have in consultancy direction. So, but apart of that, let's start talking about the main challenges with port equipment. So, as a trusted consultancy company in port verification, we can highlight one of the biggest challenges faced by customers worldwide. So this is the aging of structures and their lifespans. So basically, how to deal with old structures and how to extend their lifetime. So it's not a secret that old structures were designed according to old standards. Yeah, and before the newer standards were introduced, industry followed different national standards like DIN 15018, and then, of course, FEM standard in the middle. But the main problem was that they were developed a long time ago, basically in early 80s, and they have to be revised and harmonized to take into account more efficient design tools currently used. So, due to the use of these manual calculations, the level of detail and accuracy in design was pretty low, and very often it was resulted in the conservative assumptions. So, as a result, basically that was as a result we have a certain list of consequences. So, first of all, this is proper to perform a nice maintenance with regular inspections to make sure that basically there is no issues. And there are also others. So I propose to divide it into kind of two parts. So starting from basic assumptions. So we have following the old standards, the main idea is that the traditional hand calculation method was used, which is fairly simplified approach. So when talking about the cranes, the main assumption is that the structure is always operating under the maximum load, which is of course not true, and we know that from the experience. All structures, well, most of them were designed according to ASD method, simply neglecting the individual influence of different loads. So that provides a simplified load pattern. And when talking about the trolley, also one of the main assumptions was that the trolley is traveling between the extreme position, which is of course not true, because especially talking about the STS cranes, because it fairly depends on the size of the ships and the position of the crane. So, and when checking the fatigue in these structures, what was really omitted is that classification was considered per structural members or bigger parts, but not local welding details. Of course, this list leads to a list of consequences. And the first one is that fatigue results are given globally, making maintenance challenging. So the output of the fatigue verification according to old standards is that, okay, this is the lifetime and you have to deal with that. So it could have been provided for different structural components, but definitely not for very local details, because that is much more challenging and time-consuming process. So this all resulted into the required inspection of the full structure, because people cannot simply focus on local details, otherwise there is a high chance to overlook some parts or some problems, cracks, etc. Another consequence of this standard is the non-optimal weight of the structure. So basically many cranes or equipment, they became too heavy, resulting into the over-designed structure build. Two last items are quite connected. So first of all, the fatigue lifetime for old structure was fairly limited because of this level of the conservativity. And as the result, structure, there was a common question, and it's still basically existing. The structure is at the end of its lifetime, but it's still in operation. So how to deal with that and how much time is left? In addition to all this, we have practical problems occurred. For example, the ones which are related to the cracks, like in this example. So when the cracks is found in the original design with the length of 30 centimeters, and then just in 6 months, it became twice as long. So basically, using traditional methods or hand calculation methods and neglecting detailed calculations, we might say, okay, we can come up with temporary solutions based on experience. So we can just simply weld the cracks which appeared, drill the holes at the ends of the welds, add some extra plates, but adding some additional plates and making that locally stiffer does not always mean that this is going to be better. Like in this case, when the cracks simply reappeared and the additional ones occurred. So it becomes evident that old methods and old methods in combination with old standards, they simply do not work and do not match the expectations and the level of details people require nowadays. So at this stage, basically finite element analysis pops up, and from our end, I would describe it as simulation of the real behavior of the structure, because this is exactly what you do when conducting finite element analysis. So basically, you're simply trying to represent real operating conditions or real structural behavior by this receiving accurate stresses, displacement, internal forces per every single spot. So as an outcome, the results are obtained in detail, as can be seen in this picture. And what's more important, this is not in detail per structural components globally, but this is the level of accuracy is given per each spot. So basically on the left side, you can see a simple example of the longitudinal stiffeners being vulnerable to fatigue at the tips. And on the right side, also one of the example of the crack. So the problem with that kind of structure was that this crack was all the time overlooked, simply because it was not accessible from the outside. But after conducting FAA calculations, it turned out that there is a crack inside of the structure with the length of over 30 centimeters, which was found, basically repaired and reinforced locally to extend the lifetime of the structures. So we have multiple different examples concerning different types of structures, types of port equipment. Some of it is shown on this slide. So starting from simple ship loaders, STS cranes, jeep cranes, RMG cranes, well, different kinds of port cranes, including different configurations, modifications, also overhead cranes, various portal cranes, floating cranes, ship unloaders, stacker reclaimers, straddle carriers, ship loaders, all these kind of things, they summarize and they cause a single question: do we really need this FAA approach? And why we need? Basically, why can we not just use a more simplified traditional method following simple rules? So I would like further to touch the base of the importance of FAA with some use case examples. And of course, I would like to start from the new structures. So there are multiple standards recently developed, which are more harmonized, more specific, and which recommends to follow more detailed techniques, especially FAA. So what are the main advantages of using the FAA in terms of new structures? First of all, we conduct comprehensive verification in detail. So that allows us to check worst design scenarios and also make sure that we are doing this according to industry standards. Basically, as a consequence, we have full control over the lifetime of the structure. So it's not given per structural component separately, like in old times, but we have full control per every local spot, being able also to optimize design. So make it light, not over-designed. And what's more important, basically, it's not a black box, but having all this list of details, we provide with the reliable maintenance control. This also linked to the inspections, because instead of conducting full inspection like we're forced to in old times, we have limited inspection plan where we have to check on regular basis just several spots, making sure that they are not subjected to any local issues. So in the end, it pays off because that leads to the significant cost and time reduction, of course. So you can save a lot of material, save a lot of time on the inspection, on maintenance, and potentially save costs in the future when you want to extend your lifetime. Yeah, so it also provides with more space for design upgrades because basically, like I mentioned, you have a full control. But then there is a logical question, okay, we have new structures which are fine, but how to deal with the existing ones? So first of all, checking existing structures with FAA, we're allowed to receive all local problematic areas and also come up with clear and limited inspection plan, which I mentioned before. So you're simply trying to verify and determine the current state of the structure, inspect those points, and make sure that your FAA calculation, they match reality like they do on the pictures in the screen. So it also allows us to take into account such important factor as the corrosion. We know that existing structures, they're subjected to various types of corrosion, including pitting. So basically, you can take that effect into account, which is not possible to do with hand calculations. So like on this screen, where the plate buckling is conducted, taking into account different plate thicknesses reduced by the corrosion influence. The next benefit from it is that we can simply come up with nice design upgrades in case of any problems. Yeah, so like in this scenario, again, the same upper arm structure for the floating crane, where the up top node was a fatigue-prone area confirmed in reality, and basically the new design, new upgraded connection in the upper level was designed to implement and as a consequence, the lifetime of the structure was extended, and the maintenance plan was improved further. In this picture, you can see the evolution of the container ship size. So in both physical dimension and the capacity. So you see how the ship sizes developed over the years. So starting from 1956, yeah. So in old times, and coming up with the really large vessels. So all this, as ship got bigger, the crane used to service them did too. So, which can be seen in the picture on the right here. And what is the idea? Basically, crane owners and terminals, they face the question of how to adapt, and there weren't many options. So essentially, you either buy a new crane, bigger, or modifying the existing ones. So this created the need to modify existing cranes by increasing the height and the length of the boom, like in this case you see on the screen. So this is implemented by installing additional sections between various structural parts, like here, for example, in the upper area, where FEA plays a crucial role in verification. These sections might be installed also in the bottom level, but everything is coming down. Okay, what is the potential impact on the existing original design? So a part of such things like strength check, buckling, lifetime of the structure, various connection checks, we are also running into the stiffness aspect. So the stiffness is not directly important for strength, but when hiding the structure, it has an influence on control behavior of the crane. Yeah, so these popular standards, for example, like EN 13001, FEM, or DIN standard, they do not directly prescribe stiffness requirements, but for operational efficiency, the stiffness is very important. So typically, these values are specified for trolley riding direction, which you can see here in the picture. Yeah, so to avoid a low crane stiffness in that direction. And this situation becomes pretty tricky because even using FEA methods, there are different modeling approaches we can use. So more detailed one with 2D elements, and more simplified 1D, which is very popular among the engineering communities. So what is the drawback of this simplified approach? The drawback is that representing our supports as just one line, one stiff tube, that significantly overestimates stiffness in vertical direction. So the actual deflection is not accurately taken into account. And as a consequence, that results in 30% difference in natural frequencies between these two methods, simplified and more detailed approach. So when following more detailed approach, it has been proven by SDC that the difference between the calculated and measured natural frequencies is less than 0.2%, which basically means that these values are identical and the flexibility of the structure is well represented and can be used to estimate the structural operational efficiency we are aiming for. So, of course, there are more modifications possible. For example, starting from length of the boom over here, rail span increase in load capacity, replacement of various structural components, that can also be the case, testing of the structures, receiving CE certificate, again, in case of any major modifications like the ones concerned the load capacity. But what is the biggest benefit with FEA is that unacceptable impact on the overall design is prevented in this case, because all the outcomes are received with high accuracy. It's not limited by all these kind of modifications, which I just listed, but this is also concerning more intermediate load cases. Like, for example, in case of crane heightening or mounting the crane parts, you need to conduct various lifting conditions. For example, like in this case, when the top crane part is going to be lifted by the strength jacks positioned on top of the legs, with the pre-stressed ropes in the legs. So it is very challenging to account for the real deformation of the structure with hand calculation, because this is exactly what happens. So the legs starts to deform sideways, creating a huge displacement and creating a high buckling risk that can be prevented with FEA. Because taking into account directly the ropes, basically we are preventing the side deflection and so making sure that the buckling is not an issue. And on the other side, we also accurately determine forces in the ropes, which is a mandatory input for these conditions. And last but not least, such additional parts like strength jacks, they are also very fine because you directly take them into account in this process. So another nice example of intermediate case, which is transportation on the vessel or the barge. So barge in the current case you see in the picture. So such important impact as vessel motion scenario, it should be taken into account, which once again proves that traditional methods are not enough here and more advanced FEA approach should be used. So we are simply ensuring that all these vessel motions, they do not compromise structural integrity. All kind of CF fastening can be verified and also designed. And what's more important, we're preventing risk of failing the crane into the water. More or less analogical behavior can be accounted for the floating cranes, basically, and offshore cranes as well. So you have more or less the same effect there. So this is something, new normal, basically, which engineer should deal with every day. Additional transportation option can be done by SPMT. So sometimes you need to transport the large cranes, so you use SPMT. So normally you just give full control to the to the guys from SPMT department. However, one important thing is the local potential problems at the supports, as can be seen here in this picture. So putting the selection of the supporting area for the beams becomes essential, as it can create a local problems which require local reinforcement or design upgrades. So we have to make sure that the structure is not compromised, because afterwards it will be still in operation, and that is important. And as the result, basically we are providing SPMT transportation with a safe conditions. I also decided to highlight one more important thing, in my opinion. So this is crane relocation, a simple relocation from one region to another one. So this is this is something normal, people buying the crane and selling the cranes. However, crane relocation makes an influence on the operating conditions as well. Why? Because changing the location of the crane, we're also changing the wind zone, which is important at out of service conditions at storm. So basically these conditions, they can bring quite a lot of issues. First of all, this is stability issues. It can bring issues with the wheels and the rail, and of course structural strength problems, because still, although crane is out of operation, it's still subjected to the loads, which we somehow need to deal with. And this is a typical example, for example, what happens for zone C and zone D, which results into somewhat higher reference wind velocity. So basically with zone C, you're just fine, but with zone D, this is definitely not okay, resulting in plastic deformation. So please take that also into account when verifying your structures. Last but not least, this is dismantling and decommissioning of the structures. So basically, there are several benefits. One of them is the preventing the lifted part from falling down. But when dismantling the crane, what is important is that the COG can be shifted, so it can change depending on which parts you're cutting and chopping. This is one thing, and another thing, you involve uneven load distribution, yeah, so which makes an influence on the selection of the dismantling scheme and also the mobile cranes. So FEA approach is required to provide a safe disassembly of the crane parts here. But then there is a question, okay, we have all this kind of FEA calculations, what specifically shall we do? So there is, of course, number of checks how to prevent these issues. First of all, this is a strength check, fatigue or residual lifetime calculation, stiffness, which I was talking about, stability, plate buckling, connection check. And the only reliable method, well, one of the most reliable ones to make sure that your calculations are fine without any issues is, of course, make sure that they are done according to industry standards. Yeah, so there are multiple standards, which I mentioned briefly at the very beginning. So again, the same FEM standard, Eurocode, EN 13001, so DIN standard, also DIN VGL, FKM. So basically all kind of packages available in the market, and they all are prescribing various procedures and rules which you have to follow. So the second main challenge with sport equipment I would highlight is that FEA calculations and checks according to standard, they're complex and time consuming, which is actually true because on the one hand, you have general FEA analysis conducted for the structure. So you got a lot of different outcomes you somehow need to treat. And on the other hand, you have complex procedures according to standards. So so infinite formulas which you have to follow to check and make sure that this is all done according to correct finite elements. So the question is how to deal with that, and the answer is pretty simple. You can deal with that with dedicated tools. So there are multiple FEA packages on the market. So starting from ANSYS, FEMAPS, and Center 3D, ending up with Abacus, well known. But the biggest drawback is that all code checking programs, these are separate programs, yeah, and they require all kind of importing, exporting steps, which are time consuming. So the best solution from SDC in that case was, of course, receiving both FEA and code checking in a single package, in a single software. But that is possible, and the solution has a name. So this is SDC Verifier standalone. So basically, but before talking about it, let's refresh our minds. What is the typical workflow when conducting FEA and all these cold checks? Cold checks to receive results we've been through for the last half an hour. Of course, first of all, you need to have a model. So you need to build a model, whether it's a crane or spreader or another port equipment. Then you need to calculate loads and check all possible worst scenarios according to standards. Third step is that you have to make sure that your structural components are well determined. Because again, building FEA model does not mean that you're automatically receiving different structural parts. So what you receive is actually finite elements, and you need to recognize out of them somehow these parts. When it's done, you can of course do checks according to industry standards, so whether it's FEM or EN 13001 or any other standard, and report all these kind of things. And then last but not least step is that you did all these steps, but turns out that your results are out of the limit. So this is not according to rules. So for that situation, we developed a structural optimization tool, which you see here. Idea is that you just come up with lift host options, and then it automatically optimizes your design. And you have these arrows here. It's done on purpose, and they mean that, okay, I did so many different changes, but then I have another one. So does it mean that I have to walk through all these steps again and again? The answer is no. Basically, you just do this change in the within your environment, rerun analysis, and simply regenerate your report. And all the intermediate steps, they're repeated automatically. So I guess that sounds pretty well. So yeah, at this moment, I would like to make a poll, just as a first impression. What do you think, and would you like to use SDC right now, basically? So I'm gonna start a poll. It's already published, so feel free simply to give your answers over there. Yeah, so let's continue. So this is the workflow. So let's walk through each of these steps in more detail. So let's start from model creation. This is how the main environment of SDC standalone looks like. Basically, you have the interface is pretty convenient. So on the right hand, you have full control to the main items, but also in the upper ribbon panel, you have the same. So what is related to the geometry creation, mesh, different kind of things to create your model. Like in current case, this is the straddle carrier. So typically, in order to create a model, you start from modeling the lines and the surfaces. So we have a geometry capabilities pretty extensive. So basically, there are various options you can use to make your process streamlined. Yeah, so after creating geometry as an additional part, you would like to measure structure, whatever FEA package you use. So for that purpose, we have a meshing toolbox. Basically, it also contains a lot of nice features to fine-tune your mesh automatically. Although most of things are automated, basically you have a full control over the local details. For example, you would like to change the mesh size specifically for this area, maybe involving some quad elements, not just the rectangulars, but this is the aim in your case. So that is possible to do. So again, you have a full control over that. And as a result, basically you're ending up with the full model ready. Like in this case, this is the ship unloader, basically shown in standalone. You might ask, okay, why the hell do I need to do that? Because I'm already using some CAD software, so I would like to continuously using it. Basically, you're allowed to do so because we have an import capability. So whether you use ANSYS, FEMAP, Abacus, StatPro, Tekla, or this is a simple AutoCAD drawing or natural step file, all of these can be imported directly in SDC so that you get this geometry recognized. So all these format files are well supported. So this is briefly about the model creation. But then, okay, we have a model created. Next step is, of course, to calculate the loads. So whether it's a hoisting load, maybe some inertia movements, these pretty typical things you need to do. But apart of that, there are more complex load impact, which is briefly shown in this screen. So for that purpose, we developed a specific loading tools. So for example, starting with a wind load, which I mentioned before about, wind is actually crucial when checking a port equipment and especially cranes. At out of service conditions, old standards, they say, okay, we have constant wind pressure and wind velocity over the height. So that is relatively simplified and conservative approach. However, more harmonized standards like EN 13001, they say that the wind pressure is increasing with height. So basically that becomes already more complex because the load pattern, wind load pattern will be more or less similar as you see here in the picture. Yeah, so this is increasing with height, and this function is automatically taken into account in SDC. In addition to that, we have also wave loads, so tank ballast and buoyancy load. So you can use them in your projects as well. But then, okay, we have all loads calculated. These are just individual influences. And as you know, when following simple rules of the same, for example, EN 13001, we need to combine all these loads into the regular, occasional, and exceptional cases, ending up with multiple different load cases. Yeah, so A1, A4, B1 through B5, also these ones, and taking into account different partial safety factors, and also dynamic factors and directions of wind influence and trolley movements. Well, you're ending up with hundreds or even thousands of different load cases. So this is really time-consuming process, which you're unable to take into account by hand. Well, otherwise it will take ages, which doesn't make any sense. So for that purpose, we have several solutions. First of all, we know that engineers got used to old school Excel files, so they just build a table. They say, okay, I have my individual loads over there. I want to create load cases by linearly increasing these load scenarios. So that is possible. What you do here, you simply select your table, copy, and then paste from a clipboard so that you receive more or less things like here. But alternative solution, if you don't want to do this, you can do it from scratch directly in SDC Verifier window. If you're lazy, like all engineers are when it comes to routine, basically we have another solution which we call predefined load cases. So verifying your structures according to port equipment standards, like for example EN 13001, you're allowed to create all these load cases automatically. All you need to do is simply to determine category. For example, you have your loads applied in FEA package, so you need to give idea to the software what load category are you aiming for with this or another load. So for example, okay, gravity, this is mass of the crane. Your wind load applied as pressure, this is in-service wind load. Hoist load is just some nodal forces applied, yeah? So at the end, all these factors, dynamic impacts, they will be accounted for, automatically creating really multiple different load cases. So they can be created pretty quickly, and when it's done, basically you run analysis. And when it comes to analysis itself, this is SDC standalone is based on SimCenter Nastran solver that supports various different types of analysis. Yeah, so starting from linear and non-linear static analysis, ending up with more standard ones, like for example, normal modes, backplane analysis, and so on and so on. So basically here, you end up with first two steps effectively, but then there is a main question, okay, I have my finite element model. How shall I recognize all these structure members? Yeah, that's a huge amount of work. So we have also solution for that one. We call it recognition tools. Basically, we have separate recognition tools depending on what you need. So starting from joint and connection finder to conduct connection and joint checks, for example, according to the same Eurocode standard. Beam member finder to check beam buckling of your structural items according to FEM, EN 13001, Eurocode, these kind of things. It is possible to determine all the welds automatically, especially if we want to check capacity of the weld along with the fatigue-prone areas. And last but not least, this is a panel finder. So we're able to recognize sections, plates, stiffeners, and as a consequence, do the plate buckling checks and stiffener checks according to industry standards. So I would like to stop in more in detail on the weld finder, because this one plays a key role when verifying port equipment. Basically, like I mentioned at the very beginning, the pretty common question is how much time is left. Yeah, so how to extend the lifetime. So it becomes evident that the fatigue verification is crucial in this case, and it must be accurate. So the weld finder automatically recognizes all the welds, but it's not just simple welds. This also includes all kind of weld intersections. Yeah, so all kind of crossing connections, crossing welds. These are the weakest points in terms of fatigue. Why? Because you're ending up with the lowest characteristic fatigue strength in these areas. So this is one thing. Another thing, when using a traditional method or doing this by hand or Excel files or spreadsheets, doesn't matter, this is also time consuming because you need to convert your stresses from local coordinate systems to the world coordinate systems. You know that it is often the case that the local coordinate systems are not consistent between the finite elements, which belong to the same world part. So basically, all you have to do is to rotate your stresses into the world direction so that you take into account the world stresses in fatigue and not just stresses extracted from finite elements. So another one important thing is the weld classification. So there are different weld qualities allowed by the standard, starting from weld quality D and then ending up with B star. So these weld qualities, sorry, I think I jumped too much between the slides. Yeah, doesn't matter. I click the button. So all these weld qualities, they are defined by the standards as well. So depending on the load acting on your welded detail and also this quality which I mentioned about, also type of the weld, you're ending up with different numbers. Idea is that you need to set up these numbers to every single weld, depending on these parameters. Yeah, so this is pretty time consuming, especially if the large part of your crane is modeled, like in this case, for example. But with SDC, basically, this process is also completely automatic. Yeah, so if I zoom in to this picture, you see these multiple colors. Each color means different notch classification. Yeah, so for example, a pink, this is a butt weld I see over there, also there. The blue ones, these are the perpendicular to the weld directions, and there are also these spots you might notice, these black ones. Basically, these are crossing of the welds where you have to take into account the lower notch class, which I was talking about. Another one crucial thing is the real crane usage, which you have to consider in detail. So as I mentioned, traditional methods and old standards, they simply assume that your trolley travels from one extreme position to another one position, resulting in the highest load spectrum factor of 1. Of course, it's not true, because depending on the ship size, and the position of the crane, these things are different, and the experience shows that the extreme positions are rarely used. So that's about 10 to 15%, depending. So SDC allows to take this distribution into account in detail as well. Yeah, it's not related only to STS cranes, but also to RSC cranes and all kind of cranes, including the ones with that require multiple positions of the boom or jeep or other parts. Yeah, so basically having these things recognized, you're allowed to do checks according to standards. So SDC database is pretty extensive so far. So you have all kind of standards implemented with various checks. Yeah, so when focusing on Eurocode, for example, you have a full set of different checks. So starting from beam buckling, welds, fatigue, bolts, plate buckling checks, connections, and even the influence of the fire. So fire design rules are implemented. And yeah, any other standard is also pretty extensive, and this is all the time growing. So the biggest benefit, I think, is that all checks are open. So it's not a black box. You can simply go to any kind of check, check the formula, how it's written, where it came from. You can take control. You can edit these formulas based on the existing standard, password protect them, share with your colleagues, do whatever you want. And the only difference in these formulas is that the variables in the formulas, these are actually existing parameters of your model. So this is a huge advantage because, again, you have full control and you don't need to use any Excel files and the alternative solutions. Results are presented in two ways. So first of all, with the plot, like in this case for plate buckling check or for fatigue. And another type is the table, which can be seen here below. But like I mentioned, not everything is going smoothly. So you might need improve your design or input parameters to stay within the limits. So for that purpose, we have design optimization tool. So when focusing on this case with beam buckling of the boom, crane boom, basically, what you do, you simply come up with list of options you want to check. Yeah, so, and you give idea to the software, okay, I have 10 different properties or cross sections. I want to check them instead. And the software will determine the most optimal solution for you, and you can automatically replace it in the model as well. Exactly the same thing can be done for the plate buckling, for weld dimensions when checking capacity of the weld. So these things can be fine-tuned pretty effectively. So after these things are done, you can generate extensive report. So we have, again, you have full control over existing items. So it works like just drag and drop option. So you build your own template, which you can use further for the next project. So you don't have to redo it again and again. And at the end, basically, it is exportable to Word, PowerPoint presentation, PDF document. And also what is nice to know is that this is automatically sorted in the bookmarks or a navigation pane in the Word document can be used as well. So just summarizing, SDC works, SDC Verifier standalone works independently. Yeah, so this is very important. So you have all-in-one software solution, starting from modeling, simulation, calculation, code checking, optimization, reporting, and also having available import and export capabilities. So based on the internal research and the statistic from the clients, we see how efficient is the workflow of SDC Verifier over the different steps. For example, starting from hand calculation, working with standards, and the reporting part. So basically, when you couple these things together, and take a look at the overall picture, you see that the time saving with the help of SDC is over 50% of engineering time that can be saved in your company. So this is the huge advantage. There is one thing you might say about the maintenance, because calculation, code checking, this is all nice, but practically how to facilitate your maintenance process. So we have solution for that one as well. Its name is Structural Asset Management Tool. So this is a dedicated web-based tool that includes multiple assets in the same tool. Yeah, so if you have a terminal and you have multiple types of structures, different number of types of structures, yeah, so you have this collection of assets available in a single window, and you have full control to the details of every single asset. So a typical overview of a total asset would look like this. So basically you have location specified for your structure. You have risk level described, damage type. You see the images, and you know a reminder when the next inspection should be made. Yeah. What is also important is that it's not only about the overall picture, but this is also about the documentation. So all kind of information can be added to assets, part, location, or inspection points. For example, like in this case with reports. So you can simply upload all kind of information and have access to file functions depend on the role of the user. Yeah. So if you have inspector or engineer or admin, idea is that after logging all actions, the data is stored differently, and third-party inspectors, repair companies, they can get access to different information, which is pretty handy because not everyone needs to have an access to the full data. So these assets are divided into the parts and also inspection points. So for example, here you see the assets represented as structural parts. So I know, okay, this is my boom, bridge, pylon. Each of that has a certain health status. So whether it's critical, good, or fair or poor, basically that specify a structural component in general. But of course, you have access to more detailed information to every structural component. So basically, that includes locations of parts. Because, for example, when focusing on the boom, you might have multiple different spots which you have to inspect. For example, boom bridge connection or connection with the forestry, yeah? And each of these spots has also a certain health status. So that basically determines the overall status of the more global asset. And when focusing on the locations of parts, basically you have a full access to the points of locations. And so that becomes very detailed overview because you have a full control to, like in this case, for example, connection between the boom and the forestay. You see you have 6 different inspection points. You know their health status, and you can basically set up actions. Okay, what is the damage type? When was it inspected? You can also add more details with the pictures, save it, and at the end you get an overall overview for the global assets and also more localized ones with the full maintenance improved procedure, reminding basically when the next inspection must be conducted and what action plan has to be done. So summarizing this short presentation, first of all, I would like to start from the traditional calculation methods, which are not sufficient and must be definitely replaced with FEA. So it has been proved multiple times. Sticking to industry standard is key to safety. So this is one of the most reliable ways to make sure that your FEA procedures, steps, and results, they are done according to rules. All existing new structures, whether it's also design modified structures, transported structures, decommissioned ones, they should be based on FEA. So I think I gave more than enough examples. Well, it was short, but pretty, I hope, clear that without FEA, this becomes pretty challenging and also risky, putting a high risk hazard for persons on site. So SDC standalone provides all necessary tools within a single environment, so you don't have to jump between different tools, wasting your time. It's related to everything, so starting from modeling, FEA analysis, whether it's more simplified or a nonlinear analysis, verification according to industry standards, optimizing design, reporting these things. And the huge advantage is that the workflow is automated, so it can serve as template for future projects. If you have several cranes, several straddle carriers, spreaders, whatever, and you already conducted a certain calculation and you made a setup, you can of course reuse it further, saving time in the future. So quick and last minute design changes are finally manageable. So basically when your client or whoever it is comes with the question in the last minute when everything is done and asks to check something quick, of course you can do that because all the intermediate steps, they are synchronized and repeated without human being involved. So approximately 50% of total engineering time is saved with SDC, which I think is a nice example of the efficient tool and technique how to streamline your working process. Yeah, and last but not least, this is of course a web-based structural asset management tool that collects all kind of necessary information data that can be used by terminals and the crane owners to extend the lifetime and of course optimize the maintenance of their structures. So for now, thanks. I hope that my presentation was clear, and I see we still have a couple of minutes which we can use to answer your questions if you have any. Is it possible to simulate non-continuous welding on stiffeners? Yes, of course, because basically that is coming down to your modeling approach. So if you model your stiffeners as non-continuous welding, then it's fine. Yeah, you can do basically having stiffeners directly modeled. There are several possibilities. So you can conduct directly the stiffener check and also local fatigue check close to the welded details. Okay. If there are no questions, I'm gonna say thank you for attending the 2 days webinar. And again, if there will be any questions from your side, feel free to ask them using my email or our support email. Good, thanks again, and have a great weekend ahead.